Olivier de Weck. He's the Apollo Program Professor of Astronautics and Engineering Systems at the Department of Aeronautics and Astronautics at MIT. Professor de Weck is a leader in systems engineering research. He focuses on how complex man-made systems, such as aircraft, spacecraft, and automobiles, printers, and critical infrastructures are designed and how they evolve over time. His main emphasis is on strategic properties that have a potential to maximize life cycle value. The methods he has developed have impacted complex systems in space exploration, oil and gas exploration, as well as sophisticated electromechanical products at organizations like Xerox, Pratt & Whitney, and DARPA. The title of his presentation today is Technology Roadmapping and Development, a quantitative approach to the management of technology. Ollie, thank you for joining us today. It's great to have you as always, and the stage is yours.
Thank you, Peter. It's great to see you all. I'm happy to join with Pierre in this session on technology strategy, technology management. I think it's a critical topic. And I'll talk to you about road mapping the future of technology. Of course, I'll focus a lot on my home industry, which is aerospace. But a lot of the, I think a lot of the insights apply to other industries as well. And much of what I'm about to say is based on my book that was published in 2022. I'll basically highlight some of the key takeaways from it. The center of it, though, the central idea here is about road mapping, technology road mapping being at the core, perhaps the most important function of technology management in technology centric firms. And much of this experience is based on the time I spent as Senior Vice President for Technology Planning at Airbus in Toulouse in France while I was on the sector. They were created in 1969, really by a political decision of the German, French, and UK governments. It was an industrial policy decision to merge essentially a lot of the European companies like Aerospatiale, MBB, and so forth. And the goal in 2016, so this is like 7 years ago, was to become #1 in the aviation industry. And many of you know that at the time, Boeing was the leading producer of commercial aircraft in the world. And since then, Airbus has overtaken them for a number of reasons. The challenge was, how do you create a coherent and ambitious competitive technology portfolio? The picture that you see on this slide, I took myself at the Company Museum of Airbus in Ottobrunn, south of Munich. And I love this family tree that shows you some of the epic products, like, for example, the Concorde, a supersonic aircraft, the Airbus 300, the A380, and the latest one is the A350. I often get this question, what is a technology roadmap? The simplest way to explain what a technology roadmap is shown on this graph. It has the products at the top in red. Products come in different product lines. So each horizontal line could be a different product family, could also include services. And then in blue below that, we have the technologies that either enhance or enable these products. Technologies also come in multiple generations. They improve over time. The most interesting are the diagonal arrows on this chart. This is the infusion. These are the infusion pathways for technologies to be infused into their parent technologies. This should not just be one chart that somebody creates intuitively, but the point is that there should be a lot of thought, a lot of discussion, a lot of analysis that goes behind creating a technology roadmap, because each of the blocks shown on this chart could represent, many, many millions or even billions of dollars of investment. So to go a little bit into more details, what should a good technology roadmap look like? We created an example using, I would say, a product that is not yet a fully established market. Let's call it a proto market. And that's the market for solar electric aircraft. What's shown on this chart is the Zephyr. Zephyr actually started as a university project in the UK. It's a solar powered aircraft that can fly in the stratosphere. So it flies about double the altitude of commercial aircraft, and can provide missions like reconnaissance, imaging, communication relay for disaster mitigation, things like that. The world record was established in 2018 for nonstop flight without burning a single drop of fuel, 26 days, almost a month. And that world record has since been broken by Zephyr itself, and it's currently over 60 days. So imagine flying in the stratosphere for 2 months, nonstop, without burning a single drop of fuel. It's really impressive. So how does this technology evolve? Where should it evolve? And what does a technology roadmap look like? So here on campus at MIT, I teach a course, Technology Road Mapping and Development. I've been doing that for about 3 years. And students develop a technology roadmap on any technology that they're interested in. So Pierre was talking about generative AI, for example. Absolutely, that's within scope. Some of these are physical technologies, also life sciences. Pierre mentioned, the emergence of Cambridge as a life science cluster. mRNA vaccines is another example. We had a roadmap last fall on artificial meat, lab-grown meat, which has been around long enough to actually have a track record and figures of merit. And so there's a roadmap for lab-grown meat, if you're interested in that. So a good technology roadmap has 12 chapters. These are the 12 chapters listed here. I don't have time to go through all of them, but I'll just give you a sample of some of the sections. An overview of the technology, interdependencies with other roadmaps, a formal conceptual model of the technology, for example, using OPM, object process methodology. It's an ISO standard language, ISO standard 19450. What are the figures of merit that you use to judge the technology, to quantify its progress? An alignment of the technology with the company's strategic drivers, a competitive analysis. One of my favorite sections, section 6, you want to know, are we ahead of the competition? Are we about even, or are we lagging behind them? A technical and financial model, a list of the actual R&D activities, projects, and demonstrators that you're funding as part of this roadmap. Key publications, presentations, and patents. So what's the IP situation here? A summary of your key technology strategy in this area, including the famous swoosh or arrow charts. And then section 12, which is an assessment of the maturity of that roadmap. And that's really important when you put in place a governance in a company. Usually this is done in a chief technology office. Is this roadmap good enough to make actual investment decisions? Is it, so to speak, investment grade? So let's look at a couple of these sections in the context of solar electric aircraft. So section 1, what is the technology? What does it look like? What's within scope? So this is what a typical solar electric aircraft looks like these days. It's fairly lightweight. It has a large wingspan. The wings or part of the aircraft might be covered with thin film photovoltaics. It doesn't have usually an internal combustion engine or fuel-based propulsion. Sometimes it does have a range extender. It has a battery pack, a payload, which could be manned or unmanned, propellers or ducted fans. And of course, where does the energy come from? From the sun, from solar radiation. And as we know, it really matters the time of year that you're flying. Right now here, I'm looking out the window here in Cambridge, and it's a bright sunny day. Sunrise was at 6:40 this morning, and sun is going to set at 5:15. So still the time of day, the sunlight is less than 12 hours. And so the latitude also matters where you're flying. Let's jump to section 4, figures of merit, FOMs as we call them, figures of merit. How do you judge the quality, the performance, the cost effectiveness of this technology? Unit cost, operating cost, maximum payload, and endurance. The 4 figures of merit shown in bold, these are the key ones that the market, which is an emerging market, uses to judge competing products. And then Below that, we have other figures of merit that are more internal: energy storage density, the recharging rate, the max power of the engines, the photovoltaic cell efficiency, and the availability. How many hours per year can you actually fly? Let's jump to section 6, because now we have these figures of merit described. We can use them for benchmarking, comparing our product, our technology against that of the competition. So what you see on this chart are 7 electric aircraft. Not all of them are solar electric, but they're all electric in terms of some of their key figures of merit: first flight, the mass of the aircraft, payload, passengers, endurance, the motor power, the wingspan. And so the Zephyr is shown there. That's the Airbus Zephyr 7. Siemens has produced a very powerful electric aircraft, but it's primarily for aerobatics. The Airbus EFAN crossed the channel from England to France several years, actually for the 100-year anniversary of Blériot's first crossing of the channel. Pipistrel Alpha Electro is actually a production aircraft produced by Pipistrel, which is a quite successful company in Slovenia. They make these small electric trainer aircraft. Solar Impulse flew around the world in 17 stages. And interestingly, the Google Solara 50 that's shown here is canceled. It's a defunct project, and I'll explain why I think that happened. So if we look at this graphically, and I'm in the School of Engineering here at MIT. We like to use graphs and figures and numbers to understand things. I'm showing you the endurance versus the payload for these solar electric aircraft. And so the black line, this best trade-off between how much payload we can carry and how long we can fly, is the 2017 one. This is what was actually achieved back in 2017. And every one of these points, you can point to an actual system, an actual product that achieved that level of performance. Then we have in red the 2020 target, and in 2030, a projection of where we think by 2030 what we might be able to reach thanks to technological innovation. And so you can see there's a progression over time of what's achievable for this type of product. We saw the Google Titan Solara 50 project canceled. There was an even more ambitious one, the Boeing Solar Eagle, that was funded by the DARPA Vulture program. They wanted to fly for 5 years nonstop and carry a payload of 450 kilograms. This is more than a decade ago. And you can see that point is way, way out in the upper right. What that tells us is that was a utopian target. So one thing I recommend for business leaders and technologists is, yes, you should be ambitious. You should set ambitious targets, but do not set utopian targets, because they will backfire and actually consume a lot of resources and in the end be very frustrating. So part of my mission here in promoting technology road mapping, promoting a more rational approach to it, is helping you find the right level of ambition. If you're not ambitious enough, you're not going to be competitive vis-a-vis your competition. If you're too ambitious, meaning utopian, you're going to be chasing targets that are not realistic. So finding the right middle ground is challenging. Number 9, what are the actual R&D activities and projects we should be doing? And so for that, you need to rank order technologies. Which one is the most valuable, second most, third most? People usually don't like to do that. They don't like to rank order technologies. Who wants to be told your technology is number 9 on the list? Nobody wants to hear that. But the reality is you do have to have this kind of discussion and analysis. So one way to do this is to build a model of your product, or you could call it a transfer function. On the left side, you feed in the component level technologies and business as usual versus accelerating their development. And on the right, you predict at the mission level, at the market level, how well do you think this product will perform? And you can see the green dot there. That's a specific target for 2030. in terms of payload and endurance. The blue line is what we think is achievable without any special investment, meaning you're just buying technologies, COTS, commercial off the shelf, and you're integrating them together, and you would miss the target. You would not be able to achieve it with just COTS technologies by 2030. And then the red line shows you what the prediction is that is achievable with focused R&D investment. Interestingly, the horizontal line shown here is, I hope you can see my pointer here. The horizontal line is the energy limitation, the energy constraint, and the vertical line is the power constraint in this particular application. And so we can see that we're unable to meet the target if we do not invest at all in R&D. If we do structural improvements alone, that helps us, further lightweighting, composite materials, for example, but it's not enough. Interestingly, if we improve the solar cells, those thin film solar cells, you might be asking, where's the blue line here? Well, it's hidden behind the red line, meaning you can invest in solar cell improvement, but it doesn't actually help you at all. And why is that? Because solar cells are already good enough. They are not an active constraint in the system. So any technological investment you make needs to be targeted at a bottleneck or as an active constraint in the system. And the solar cells are not the active constraint. What is the active constraint is the batteries, the ability to store enough energy, because remember, you're not landing, you're not refueling, so you have to make it through the night on the energy that you've stored during the day. So basically, the most important investment here is, in this case, we're choosing lithium sulfur batteries instead of lithium ion batteries. Lithium sulfur batteries have higher energy density, but they don't have as many cycles as lithium ion batteries. So that's where we'll target our investment. And then that leads to section 11, which is our tech strategy, which is targeted development of a solar-powered, electrically driven unmanned aerial vehicle, a HAPS service platform. HAPS stands for High Altitude Pseudo-Satellite. That's also another word used for these airplanes. We want to do an entry into service date of 2030. We would like to achieve an endurance of 500 days and a useful payload of 10 kilograms, because that actually provides a valuable service. To achieve this, we're going to invest in two major projects. One is a flight demonstrator with a first flight by 2027 to demonstrate a full year aloft with a 10-kilogram payload. And our second investment will be an accelerated development of lithium sulfur batteries with our partner XYZ. We would like to partner here with a company that has expertise in lithium sulfur chemistry. And we're going to look at 500 charge discharge cycles and have this technology ready at TRL, technology readiness level 8 or 9 by 2027. So you can understand now how this tech strategy was derived, not just by intuition or pure discussion, but by careful analysis. Okay, so that's kind of an example of a tech roadmap. I want to stay in aviation for a second and talk about a bigger time horizon and more commercial aviation that you're all familiar with. So beside the Zephyr world record that happened in 2018, another really exciting event was the first entry into service of this airplane shown here. This is the A350-900 ULR, ultra long range version. The lead customer here, Singapore Airlines. So one of the routes they fly is Singapore Changi Airport to New York. The famous flights SQ21, SQ22. That's essentially an 18-hour flight nonstop. And whenever you talk about technology progress over time, you have to also mention what's your datum? What's your reference point? So I want to use the DC-3 as a reference point in 1935. Why the DC-3? Because it was the airplane that really launched commercial aviation as we know it today. So if we compare those two airplanes that I just showed you, the DC-3 in 1936 and the A350 in 2018, you can see that they're pretty far apart, right? On this payload versus range space. By the way, payload versus range, this is the chessboard, the market segmentation, the chessboard of aviation, of the aviation industry. If we multiply payload by range, we get this figure of merit called RPK, revenue passenger kilometer. And that's what's used in the industry. So let's do some quick calculations here. A DC-3 in 1936 carried about 20 passengers for about 1,500 kilometers. That's 30,000 RPK. An A350 today carries about 170 passengers over 18,000 kilometers. That's 3 million RPK. If we take the ratio of those two numbers, that's the improvement factor we've seen over 82 years, and it's almost exactly 100. We can say that civil aviation has improved by a factor of 100 over 82 years. And then if we apply Moore's law to that, Moore's law says, the generalized Moore's law says, there's an annualized average percent improvement in technologies. It's about 5.8% in commercial aviation. And some of you might say, wow, that 5.8%, that's not a lot. That's not really that impressive. But remember, it's 5.8% on average consistently over 82 years. That is really impressive. And when it's like compounding, right? Interest in a bank account. That gets you the 100-fold improvement over 82 years. That is really impressive. And that's for range and payload, but we've seen similar improvements in safety, operational reliability, cash operating cost, and the new battleground. This is when disruption happens in industries, is when the key figures of merit shift. The new battleground is going to be emissions, the sustainability. I promise you not too many equations, but this is an MIT ILP seminar, so we have to have at least one equation here, right? You got to drink a little bit from the fire hose. This is the first equation that we teach in our department, the famous Breguet range equation. Breguet was a French aviation pioneer. He was a pilot, he was an aircraft builder, and he was a scientist. So he came up with this equation, derived it from scratch, which predicts the range of an aircraft that is burning fuel as a function of these different factors. So how much energy per mass of the fuel? Earth's gravity, we can't change that. We have, by the way, flown on Mars now, right? So if you did this for Mars, you'd have to replace Earth gravity with Martian gravity here in this equation, which is about 38% of our gravity. L over D, lift over drag, aerodynamic efficiency, propulsive efficiency, and structural efficiency. And we can rewrite this equation using SFC as a parameter. SFC is the mass flow of fuel per unit of thrust. And I'm going to come back to that in a second. So the question is, okay, 100-fold improvement in aviation in 82 years, who deserves the credit or most of the credit for that? Structural people, aerodynamicists? Well, the answer is propulsion, air-breathing propulsion, people working on engines. 60% of the improvement is due to engine improvement. And this chart here shows you, so in this case, the y-axis is lower is better, less fuel consumption. And then the horizontal axis shows you normalized complexity. Complexity of these engines is a function of the number of components, their interfaces, and also the interactions between the components. And so we've gone from turbojet engines, where all the airflow goes through the core, to single stage to multi-stage engines. We've created bypass flow engines. So typical bypass ratio in this day and age is 10-1. So most of the flow goes around the core. And the latest generation are the so-called gear turbofans. So more performance, more efficiency, but we had to buy that with a lot more complexity. So this is what one of those new engines looks like. This is the gear turbofan. This particular version is created by Pratt & Whitney, not too far from MIT in Connecticut. And the magic sauce here is in the front of the engine. It's this gearbox that decouples the low pressure spool from the fan. It's a 3-to-1 reduction ratio, but it also has a lot of additional software, lubrication, and so forth. but it's that really allows this efficiency. And that also led to a huge commercial success for Airbus with the A320neo new engine option family. So we've looked at technology progress over time in quite some detail. So when you look at it for these engines, these air-breathing engines, as one example of technology, you can see a flattening curve. And what the flattening means is that as the technology matures and gets better, it gets more complex, and every % improvement that we're trying to achieve is costing us more and more in terms of the additional complexity we need. So as a technologist, as a company, as a business, you should be aware, where am I in this particular curve, right? And why is that important? It's because when we think about technological disruption and displacement over time, technologies start substituting for each other. And one model for that I personally believe is correct is these S curves, right? Every technology has an S curve. And the question is, one of the key questions in technology strategy, which is really the topic of this webinar, is when is it time to switch, right, to the next S curve? And when do you, because if you want to switch when it's already clear that the crossover has happened, it's too late. You're not going to be a leader. You need to pre-invest before the switch actually happens. So here are 3 examples of these S curves. Computing, we went from mechanical computers to solid state relays, vacuum tubes, transistors. Today, we're in the age of the IC, the integrated circuit. And what's the future of computing? Optical, DNA, quantum, question mark. Propulsion, we just talked about it. We had piston engines initially, then turbojets, then turbofan. Now we're moving to hybrid electric propulsion, and perhaps the future is hydrogen fuel cells. Peter, our host here, is Swiss originally, and so am I. And as you know, Peter, what are people in Switzerland obsessed with? Peter.
Chocolate and watches, I guess.
Right. One thing you learn in Switzerland when you grow up is be on time. Do not be late. Being late is a capital offense. So timekeeping is essential. So here are different technologies in timekeeping. Sundials, mechanical clocks, quartz, atomic clocks, and now we have quantum clocks, right? And so this is really the question, is these S curves. So let me show you one of the big topics at Airbus when I was there, and it's still a big topic, is what about hydrogen replacing kerosene as the primary fuel? Is that going to happen? Should it happen? Who's going to be leading that? And Airbus clearly decided to be a leader in hydrogen propulsion. Maybe it won't happen, but if it does happen, it's better to be the leader than be the follower. And so I wanted to show you this program here, the Zero E program. Zero E stands for zero emissions, is really what came out of our technology road mapping efforts using this approach. There's 3 platforms under development, a turboprop, blended wing body, and a turbofan. They tend to be for the shorter to mid-range here. And a lot of investments are going into hydrogen-based aviation these days. And I just want to show you a very short, it's kind of a promotional, but it's a very short video just to show you how cool this is and what those platforms might look like. So hopefully this will work. Okay, so 2035, that's well, that's like 10 years from now, right? 11 years from now. That's the That's the anticipated entry into service of this new technology. So to wrap up, because I know we probably have some questions, Peter, I guess, hopefully that have come up. This is in a nutshell the framework, this technology road mapping and technology planning framework that I've developed and that we implemented at Airbus. And I'm working with several other organizations now, including NASA, Draper, some commercial companies as well, on implementing this approach. 4 key questions in the center. Where are we today? Where could we go? Where should we go? Where are we going? On the left side, you feed that with a clear decomposition of products and services and technologies. You map them. Human input. This is not just a kind of a black box magic. Technology scouting, IP analytics, and your human experts are critical as well. And then the company's strategic drivers feeding into it. On the right side, you get your outputs. So these charts, these roadmaps that show where do we fall as a company, who are our key competitors, are we ahead, behind, about even when it comes to these figures of merit. Different scenarios, scenario A, scenario B. Scenarios will scramble, different scenarios will scramble the rank ordering of technologies. If you think about like high fuel price, low fuel price, with carbon tax, without carbon tax, that has a big impact. And then finally, in the lower right corner, your Pareto front, your efficient frontier of different portfolios, some more conservative, more incremental, or more ambitious. So to conclude here, I hope you got some insights into what technology road mapping is, what a roadmap should look like. Many of the examples that I gave you are from aerospace, but it applies pretty broadly. And so if you haven't seen the book, it came out in June 2022. It's done pretty well, and I'm happy to answer any questions you may have.
Great, thank you, Ollie. Really excellent, and I like the instructive examples. So we got a couple of questions here. I think I just go in the order they came in. The first one is actually very interesting, a very pointed questions. How can your skills be applied to direct air capture, since we need to go back to the original 0.027% of carbon dioxide content until 2050 to have a lively world for our children?
Yeah, it's a great question. And so it so happens that direct air capture was a roadmap that was developed as part of my class. I'm going to a website here that, if I may, this was unrehearsed. So if you don't mind, I'll just share this with you right now. I put a link in the chat. This website, it looks kind of like Wikipedia, but that's what we use with the students as well to create their roadmaps. They can choose any technology that they're interested in. So we have a direct air capture roadmap here. And basically, as you can see, it has the 12 chapters that we just talked about. You can see the carbon abatement costs. So I invite you to go through this direct air capture roadmap, and it has a 4-level hierarchy of technologies. And there are several different methods for capturing CO2. All of them have certain advantages and disadvantages. And eventually, what we care about is the figures of merit are interesting here. Dollars per ton of CO2 captures are removed from the atmosphere, the scale of a plant, so gigatons per year. How much energy does it take to remove the CO2? Kilojoules per ton. How much land demand, right? Land area is taken up for CO2 removal. And then what's the efficiency of the process? And so you can see the predictions here for the levelized cost of capture. We talk about LCOE, levelized cost of energy, and here it becomes LCOC, the levelized cost of CO2 capture. Anyway, I don't want to go too deep into this, but you're welcome to take a look at this direct air capture roadmap.
Well, interesting. So could you actually bring road mapping to almost the next level, right? To apply to climate change? What do we need to do to get back to the CO2 levels we want to be at in 2050, right? Beyond direct air capture.
I think climate change as a whole is probably a bit too broad. You know, that's like a global challenge that needs to be decomposed. But
Yeah.
what I feel comfortable saying, Peter, is that we can group and classify technologies. And in fact, I didn't talk about this during the presentation, but I can show it here. This technology matrix, it's a 5x5, I think is a very rational way of classifying and grouping technologies. So what does this show us? In green, the row is the operands. What is the technology actually operating on? Matter, energy, information, value, which means money essentially, and then organisms, life, right? On the right here. So traditional engineering is matter, energy, information. But now recently we have value and organisms. And this column here where I'm pointing is what we call fintech. And that fifth column is what we call biotech, right? And then the 5 processes are transformation, transportation, storing, housing, exchange or trade, and control and regulation. And as you can see, I mean, we've created not quite 100 roadmaps yet, but this is pretty well populated. We still have some blank spots. So if any of you have technologies in those blank cells, I'd love to hear about them. But it's been so to address climate change, I think we need a mix of these technologies.
Yeah, very good. Let's go to the next question, and that is, isn't DARPA's role to initiate utopian projects, right? But I know you have been involved in DARPA projects, most likely with road mapping, right?
Yeah. I've worked probably on half a dozen DARPA projects in the last 20 years. And you know, yes, the role of DARPA is not to create utopian technologies. Because if that was the role of DARPA, they'd be working on things like teleportation, right? The role of DARPA is to create strategic surprise, prevent and create strategic surprise. So it should not be utopian. It should be challenging, a stretch goal, disruptive. But in the end, you have to produce a prototype, a demonstrator, and it has to be beyond the current state of the art, obviously. That's what surprise implies, but it can't be utopian. And so some DARPA program managers, because it's in the end, it's up to the program managers to pitch their ideas, get them approved by DARPA leadership and the DoD, really understand this well. And they've done a great job defining new areas and setting the bar high enough, but not too high. And honestly, other DARPA program managers haven't done that well. And it's more like science fiction, and they've set cool ideas, disruptive ideas, but either not feasible physically or way too ambitious. And in that case, it's very frustrating because, you know, we're wasting millions of dollars. And maybe, you know, decades later, these ideas get picked up again. But within DARPA, I've seen big differences between different programs.
Yeah. I guess being disciplined and applying road mapping, right, is probably will help to be more concrete and arrive at a successful outcome of a project.
Exactly.
So let's go to the next question, which is, thanks for your presentation. You can share your view on setting goals for a technology strategy proposal. Specifically, what kind of margins should be applied for cost, performance, and schedule? Well, that might be a little bit too specific, but
no, I think
say something to it.
I understand. So ultimately, technologies are developed one project at a time. That's absolutely true. Every project is subject to the famous iron triangle, right? Cost, scope, and schedule are in tension with each other. And especially the more ambitious, the more early, the young to mid TRL technologies, you don't know what's going to happen. The failure modes, the real purpose of technology maturation is to uncover address failure modes of the technology. And by definition, you don't know what all the failure modes are going to be. When you bring the technology out of a protected laboratory environment into real applications, real demonstrators, a lot of things will go wrong. And you do need a margin, whether it's 20%, 30%, 50%. I don't think I can answer that in a general sense, but you absolutely need to reserve budget to address these failure modes during tech development.
Okay, next question. When looking at technology road mapping, do you recommend a roadmap for each product or product line, or is there a way to transfer this to an organizational level?
What I recommend is a hierarchy. So when you go look at the roadmaps that we've created, you'll see level 1, level 2, level 3. Level 1 is often a kind of organizational business unit type roadmap. Looks more like a product roadmap, right, than a technology roadmap. So that's where the markets, the product lines, the services, the business unit interests are often encapsulated in a level 1 roadmap. And then we can argue, is that a tech roadmap or is it a product roadmap? It's semantics. The actual technologies that enable those are at level 2, 3, or even level 4, for very detailed technologies. The key is that you create that clear decomposition. Many companies don't have a clear decomposition and classification of what they do and how things hang together. So that is step 1, is to create that clear decomposition.
Okay, very good. Next question. Why are the hydrogen-powered aircraft so slow? I'm not sure if that person make an assumption, but
I do think there is an assumption. You could fly we use liquid oxygen and liquid hydrogen for rockets, right? And they're supersonic. They go to Mach, more than Mach 10. So just the fact that you're using hydrogen doesn't mean you're going to be slow. But what is probably true is that the optimal cruise speed of a hydrogen-powered airplane is going to be lower than the current. The current optimal cruise speed is like around Mach 0.83, Mach 0.84. We've kind of converged on that over the decades. Because hydrogen, particularly if it's gaseous hydrogen, has more volume, the airplanes are going to have a bigger tanks to hold the hydrogen. Bigger tank means more cross-sectional area. More cross-sectional area means more drag. Drag goes with velocity squared. Power goes with velocity cubed. So it's quite likely that the optimal cruise speed is going to be slower, but not a lot, not like half the speed. So maybe instead of Mach 0.84, we're going to be cruising at Mach 0.7 or something like that. And quite frankly, with the quality of, and then the airplane will have more volume inside, the cabin will be more comfortable. Now we're having more and more high quality Wi-Fi. I don't know if you saw in the news, Hawaiian Airlines is now going to use Starlink during flights. So I would rather get there 20 minutes later, but have a lot more volume and high quality Wi-Fi during my flight. I don't know if the person that asked the question would agree with that, but that would be my preference.
It would be my preference too, Ollie. Well, so we are coming up on the hour. Thank you very much. I think we need to stop here. I want to thank the speakers again for their presentations. And I want to thank you, the audience, for your time and attention. We hope you found today's presentation informative. Any feedback or interest in a follow-up with the speakers, please let your program director know. Thank you for joining today and hope to see you again soon at one of our future events. Goodbye.